Hi, today we'll talk about transformation of functions, and it's a continuation from yesterday's class where you looked at compression, stretches, and for both vertical and horizontal on functions. So today, even functions, the function is even if f of x is equal to f of negative x. I'm going to show you what that means in a second. And if a function is even, then it's symmetric across or along the y-axis. Examples are y is equal to x squared, y equals x power 4. Those are symmetric functions, and I'll show you in a bit why those are symmetric. If I have y equals x squared drawn on this graph, it's passing through the origin. It's symmetric because when the x value is 1, the y value is 1. But when the x value is also negative 1, the y value is still 1, because negative 1 squared is also still 1, just like positive 1 squared is 1. When the x value is 2, the y value is 4. And when the x value is negative 2, the y value is still 4. Just forgive my accuracy, because 2 squared is the same as negative 2 squared. So those functions are called symmetric. They're symmetric across the y-axis, and they're called even functions. That's what an even function is. The graph of y equals x to the power 4 looks something like this. This is x-axis, and the same thing, it's also symmetric about y-axis, because if you look at it, y equals x squared. If you put negative 1, you still get 1. If you put positive 1, you still get 1. So functions like that are even. A function is odd if f of x is equal to negative f of negative x. What that means is if two reflections f of x is equal to negative f of negative x, if two transformations happen on this function and it still ends up looking like the original function, then it's an odd function. Those functions are symmetric around the origin. This I usually prefer to write as f of x equals negative f of negative x. It is the same thing, so don't be confused by that. It's just one last step here, f of x equals, but if I combine them, it's the same thing. So let me show you what that looks like for an example like this one. If I have y is equal to x, this function y is equal to x, this is the y-axis, this is the x-axis. We're saying that the function is odd if the initial value of the function, the initial output value, is the same after doing these two transformations, this transformation and that transformation on that graph. So let's see. This first one means you're reflecting across the y-axis. So the reflection of this will be expected to be on the left-hand side of the graph, which will be here. The reflection of this one will be reflected to be on the right-hand side, which will be there. So this is a reflection along the y-axis. This is a straight line, by the way. One line, it's not 10 lines. And after that reflection, we have another reflection across the x-axis. So what we have now is that line, and we want to see if when we reflect it across the x-axis, it will take us back to the original function that we started with. The reflection of that section of the graph will be up there, and the one for this section will be down there, because I'm reflecting it across the x-axis. So I hope you can see that this green line is looking just like the red line that we started with, and the final function is the same after undergoing two transformations, the reflection across the y-axis and the reflection across the x-axis. So every time this is true for a function, we say that that function is odd. Example, I want to figure out if this function is odd. Now, just by looking at the powers, I can predict that this is going to be odd. But let's go through the math. If we want to check if it's even, odd, or neither. If it's even, then f of x will be equal to f of negative x, meaning that when I switch the input value, then the output value of the function should remain unchanged. So let's see if that's the same thing. If I switch, instead of x, I put negative x cubed minus negative x, Does that leave the output value unchanged? No. What I've ended up with is different from what I started with. Therefore, that function is not even. Let's continue to check if it's odd. If it's odd, f of x will equal the same thing after these two transformations. Now, I've already seen what f of negative x is, because that's what I was trying to find here. So I'll just substitute it inside negative x cubed plus x, and when that negative sign enters inside the bracket, I have positive x cubed minus x, which is the same thing as what we started with. Therefore, this function is odd. Look at another example. This one, again, looking at this, I can predict that it's going to be even, because this doesn't have any x next to it, but I'll still check the process. If it's even, then f of x is going to be equal to f of negative x, meaning if I switch the sign on the input value, the output value will remain unchanged. Let's see if that is true. Negative x squared minus 4, when I work it out, I still end up with x squared minus 4, same thing as what I started with. Therefore, this function is even. What about this one? Is it even, is it odd, or is it neither? So if it's even, f of x will equal to f of negative x, meaning if I substitute for negative x in place of x, I should get what I started with. Negative x plus 2. I can clearly see that this one won't give me what I started with, because I'll end up with x squared plus minus 2x minus 2x, this is x, plus 2. So that is not the same as what I started with, so the function is not even. Let's check if it's odd. If it's odd, f of x will equal negative f of negative x, which will equal negative. F of negative x is already x squared minus 2x plus 2, and then if I put the negative sign inside that bracket, I will have this output value, which is not the same as the output value that I started with. So the function is neither even, it's not odd. Those functions are usually not symmetric, meaning you cannot cut it in half, right, at any point. An example is here. I have a parent graph. Now, the parent graphs are the ones on page 5 of your workbook. They are the mothers or fathers of all of these other graphs. So, the parent graph from which this graph that I see here came from is y equals x squared. Now, things were done to that parent graph so that it became what I see on the grid. So, I'm trying to figure out what happened to this poor parent. So, initially, its origin was right there, but it was moved 1 unit to the right and 3 units down. And I hope you remember that moving the function 1 unit to the right is the same as subtraction 1 from the x value, and the 3 units down is minus 3. So this is the equation of the graph that I see on that grid. This one, I hope you can tell that its parent or grandparent is the function, the absolute value function, absolute value of x, which looks like this. And I hope you also remember that that parent graph had a slope of 1, 1 to 1, 2 to 2, 3 to 3, negative 1, 1, negative 2, 2, negative 3, 3, and so on. Its slope was 1. This one, its origin was here. It's been moved 2 units to the left, 1 unit up. So I know that moving 2 units to the left is x plus 2. Moving 1 unit up is 1. But there's something missing here, because the slope of this new graph is no longer 1. It is instead a half. That means the y values were compressed by a factor of 1/2. So I'm going to put 1/2 here. Why am I saying they were compressed by a factor of 1/2? Because here, when x was 1, y was 1. When x was 2, y was 2. However, on this one, if I kind of brought it back to its origin back here, before the what? I kind of brought it back to its origin. It's a bad estimation. This is what it would have been. Going through there. I hope you can see that in this one, when the x value is 1, the y value is 0.5. When the x value is 2, the y value is 1. So it's as if the y values are being reduced by a factor of a half. That's why I'm using this factor of a half here in front of the equation. So my equation is simply b plus 1. That's what was done to that parent to give the graph that we have in the grid. This is another one. I want to figure out what happened to this parent so that they give birth to that child. The parent for this graph, I hope you can identify that it's y equals x cubed, which looks like this. Now that parent, I can tell from the beginning that it underwent a reflection across the y-axis to make it instead look the other way, right? Now, while looking the other way, things were done to it again to have it shifted 2 units to the right and 1 unit up. So it's already a negative, right? But it's moved to the right 2 units, that's negative 2, and it's moved up 1 unit. This is the equation of the graph that I see on that grid. Moving on. So I want to graph this equation, and I also hope you can see that its parent was y equals x squared. That's its parent. But what's happening to it? It's being moved 3 units to the right, to the left, sorry, because it's positive. The output value is being multiplied by 5, and then after all of that, it again undergoes a movement of 3 units down across the y-axis. Now, on this parent graph, there are some key points. One of the key points is here. When x is 0, y is 0. We put it in the table. On the parent graph, y equals x squared. When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 4. When x is 3, y is 9, and so on. When x is 4, y is 16. But on this new function, because it is being moved 3 units to the left, and then output value is multiplied by 5, this new function, let me call it gx, this output value, things are going to happen. It's moved 3 units to the left, so this stretch, vertical stretch, and this negative 2 are the ones that have an effect to the output value. These 3 will have an effect only to the input value. So the inputs for gx are also going to change. Instead of 0, you will have, let me do another table here. Instead of 0, you don't have to draw a table every time. Really, I'm just using it because some people like the visual, but I'm also going to show you how you can just draw it without having to draw the table for it. Instead of 0, that input value is going to be negative 3. Instead of 1, that input value is going to be negative 2. Instead of 3, 0. Instead of 4, 1. The output value, remember, it's multiplied by 5, and then 2 is subtracted from it. Or it is straight 5 units, and then moved down 2 units. So the output value, which was supposed to be 0, is multiplied by 5, which is still 0, and then moved down 2 units. Output value, which was supposed to be 1, is multiplied by 5, then moved down 2 units. Multiplied by 5, 20, moved down 2 units, 18. I don't think that will fit on my graph. So those are enough for me to plot this. And since I know that it is symmetric, across this time it will be symmetric on the line x equals negative 3, I can plot it now in 1, 2, 3, and then 1, 2. That will be my first point. Then I'll have x is negative 2, y is 3, 1, 2, 3. That will be my other point. since it is symmetric around this line, which would have been the y-axis, but it was moved 3 units to the left. This is symmetric around that line. I know that this stem point will be here, and I can draw my graph like that, right? But like I said, you don't have to use these tables if you don't have the time. You can just look at the graph and know that this point, the intercept, is going to be moved 3 units to the left. Output is multiplied by 5, so 0 times 5 is still 0, and then move 2 units down. So it will end up here. Then the first point, which would have been this point, is moved 3 units to the left, so 1, 2, 3, multiplied by 5. 1 times 5 is 5, so 1, 2, 3, 4, 5, and then move 2 units down, which is 1, 2, end up there. The next key point on the old graph would have been here, because the old graph would have looked like this. The next key point would have been here. That key point is moved 3 units to the left, 1, 2, 3, 5, multiplied by 5, so 2, 3, 4, 5, sorry, 1, 2, 3, 4, 5, and then move 2 units down, 1, 2. Yeah, this point is supposed to be here, bad counting. So I hope you can see that you can still graph it without drawing all of those tables. I just use the table for, to help with the explanation. So my graph still ends up being like something. This one, the parent graph for this one, I just need to graph this. I can see that the parent is x cubed, okay? That x cubed has a horizontal stretch on the input value of a quarter. Now, to be able to explain this well, I'm going to use the tables again, but like I specified, if you understand it, no need. Now, the input values are being stretched by a factor of 4, and I'll show you why this is a factor of 4. So, initially, for the parent graph x cubed, when x was 0, y was 0. When x was 1, y was 1. When x was 2, y is 8. When x is 3, y is 27. But for this one, I'm looking for, let me call it gx again. I'm looking for the input values that will give me the same output value. So I'm asking myself, what input value of this function, this initial function, will give me the same output value of 0 in this new stretch function? I hope you can see that for 0, that will stay the same. But in order for me to get 1, an output value of 1 in this new function, the input value, I'm going to look for an input value that can be multiplied by a quarter to give me an output of 1. And that input value is 4. Alright? In order to get 8 in this new function, I'm going to look for an input value that is multiplied by a quarter to give me 8. Right? An input value that's multiplied by a quarter to give me 8. That input value would have been 16. No, hopefully 8. Sorry about that. I confused myself. I'm looking for an input value in this new function that will give me the same output as this value in the original function. So the input value that I'm going to multiply by a quarter to get an input value of 2 in the old function, so right here I should have a 2, is 8. That's why I have 8 here, right? And the next one would be, because this input was 1 or 0, this one was 1, but remember it's stretched to give me 4, this one is stretched to give me 8. The next one would have been, what input value in the old function do I multiply by a quarter to get 3? because 3 is the input in the old function that corresponds to 27. So in the new function, what input value do I multiply by a quarter to get 3, which gives me the same output? That would have been 12. Now, because this parent is stretched and then 1 is added to it, it's being moved 1 unit upwards. So I'm just going to add 1 unit to the output. 0 plus 1 is 1. 1 plus 1 is 2. 8 plus 1 is 9. 27 is 28, but I won't even consider that because it won't fit in my graph. I'll start graphing. When x is 0, y is 1. When x is 4, y is 2. 1, 2, 3, 4, y is 2. And when x is 8, y is 9. 5, 6, 7, 8 would have been here. Y is 1, 2, 3, 4, 5, 6, 7, 8, 9. Would have been up there. On the opposite side, something is going to happen. When x is negative 4, y will be positive 1. I hope you can see that if you work backwards on the other side. Because on the negative side, if you add 1 to, if the graph is moved up 1 unit, then it's going to be 4 to negative 1, not 2. This is 1, 2, 3, 4. Basically the opposite of what's happening here. What's happening on this side is the same opposite, because we know this graph is symmetric. So since this point is 1, 2, 3, 4, and 1, 2, then this one will be from this point. Sorry, it's 1, 2, 3, 4, and 1. This one will be 1, 2, 3, 4, and 1, 2. 1, 2, 3, 4, 1. Because it's moved 1 unit upwards. And then the next one will be somewhere down here. And yeah, so it's going to come like this. I hope this makes sense. You can draw it with decimals to see that it looks the same as that. Alright, your turn. Enjoy your homework. If you have questions, send me an email if I'm taking too long to respond to your private comments.